Hello, everyone. Welcome back. On behalf of the Russell Sage Foundation, the Alfred P. Sloan Foundation, and Princeton University, it's my pleasure to welcome you to the Summer Institutes in Computational Social Science. Welcome to everyone here at Princeton. Welcome to everyone at the partner locations. And welcome to everyone tuning in on the live stream. It's my pleasure today to introduce our guest speaker, Annie Liang. She's an assistant professor of economics at the University of Pennsylvania, where she's also affiliated with the Warren Center for Network and Data Science. This is actually Annie's fourth talk this week, which tells you that she's a high demand speaker, and she's actually on her way somewhere else next week for another talk. And part of the reason that Annie is such a sought after speaker is that her work is so interesting, and it's at the intersection of a bunch of things that all of us in this room are interested in. So her angle into computational social science is really about bringing together economics and computer science. And the activity that you all just did today about the Fragile Families Challenge, I think is a great warm-up for her talk. A lot of her work has been thinking about prediction. How can we use prediction in the social sciences, not just to do prediction, but to help advance theory and help advance understanding. So with that, I'd like to welcome Annie.
Hey, thanks very much, Nat. So I'm really delighted to be here at this workshop. It really seems like a very special summer program, so it's nice to be a part of it. Most of my talk today is going to be about this project that's joint with Drew Funenberg, who's an economic theorist at MIT. But I wanted to begin by just speaking a bit about the larger context in which our problem emerges and telling you a little bit more about that. Okay. So the basic setting that we're interested in is that of prediction problems, by which I mean there is some outcome that you want to predict based on a set of observables. Okay. One classic instance of this problem is predicting an individual's future wages based on an observation of, say, his educational level, parental income, and other covariates. Okay. A rather different problem that comes from game theory is predicting the actions that players will choose in a given strategic interaction, for example, described by a payoff matrix. Now, each of these problems can be described in the following framework. What we have access to as the analyst is some set of observables, okay, which lives in some sort of feature space. And we would like to predict an outcome y. We can think about a prediction rule as some sort of map from those observables into either a direct prediction of the outcome itself or potentially into a distribution over the outcomes. Now, each prediction rule is going to specify essentially a very specific relationship between the observables and the outcomes. And an important question then for doing analysis is how do we actually come up with this prediction rule? Okay, now, one approach is just to get a lot of data. So we might see many instances of observables and outcomes, and learn from that the structure of the relationship between the observables and the outcome. Okay, now in practice, we tend not to give ourselves completely up to the data. We actually try to impose some restrictions on the structure of this prediction rule G ex ante. Okay, so specifically, what we might do is define a model class. So this is a set of prediction rules parameterized by this parameter or a set of free parameters. And this model class is fixed in the sense that there's nothing the data can do to cause us to go outside of the model class. Now, if we're choosing within the model class, we're going to let the data decide that. Okay, so we get data. Maybe the model class is linear functions, and the data would tell us which coefficients for this linear function we want to use. Okay, so the data is going to reveal to us a best fit parameter, theta star, and then we're going to use the associated g theta star for prediction out of sample. Right. Now, why do we want to begin by imposing some restrictions on this prediction rule? Right? Why begin with a model class G instead of just allowing for arbitrary prediction rules and letting the data completely govern our final choice? Okay, so one practical concern is just overfitting. Right? We know that if we start with a fully flexible model class, but we have a finite set of data, okay, potentially even small, then the function that we're going to learn is potentially going to be chasing after noise. It's not necessarily going to be revealing the true structure of this underlying relationship. Okay, so that's one reason to start with restrictions. A rather different reason to begin by restricting yourself is a concern for interpretability. Right? So if you just care about prediction, that's fine, but oftentimes as researchers, we actually want to have a model class that captures some sort of narrative or insight that we think is revealing about the domain. And certainly we often want to have a final prediction rule, G theta star, that we can actually understand and interpret. Okay. So this concern for interpretability I want to think of as imposing a constraint that's actually rather different from the constraint that's imposed by concern for overfitting. And a simple way to see that is that this concern for interpretability is not necessarily indexed to the quantity of training data that you have. So even if you have a very, very large training data set, in which case the overfitting concern is alleviated, you might nevertheless want to begin with a relatively small model class that is going to be, again, simple and interpretable. Right, so just to caricature this, we can think about model classes as living in some sort of two-dimensional space, where one axis is interpretability, and then a second axis is the predictive capability of that model class. So we might think about traditional models as living at a point like this. Right, so they tend to be high on interpretability, and we hope they're also predictive, but potentially they're not the most predictive. In contrast, machine learning has traditionally optimized solely for predictive capability, without really a corresponding concern for interpretability. And we can think about the corresponding black box algorithms as living at a very different point on the space, which is high predictiveness, but potentially very low interpretability. And the fact that they're so uninterpretable has caused many to think about these black box algorithms as essentially not that useful for modelers. Right? So maybe if you're working at Amazon and all you care about is having accurate predictions, then black box algorithms are great for you. But for researchers who actually really care additionally about having some sort of understanding into their domain, these algorithms aren't that useful. Okay, so that's one perspective. And in starting this project, Drew and I were curious about whether we could use machine learning algorithms not just to help towards this first goal of higher predictive accuracy, but additionally towards the secondary goal of better understandings into the domain, or higher interpretability. Okay, specifically, we might obtain this by using machine learning to help us identify new patterns, or by using machine learning to help direct us towards simple low-parameter extensions of existing models. Right, returning towards this figure, right, essentially, we think that there is some sort of trade-off between interpretability and predictiveness, but we don't exactly know the shape of that trade-off curve, right? And very well there might be some other model class which is more predictive than the model classes we're already using without so much of a sacrifice in interpretability. And if there is a model class like that out there, the question is, how do we identify it, right? How do we go on searching for it? And our goal is going to be to try to use some of these black box algorithms to direct us towards these reasonable, moderate interpretability, high predictiveness model classes. All right. By the way, you guys should feel very free to ask questions as I go. And so just go ahead and interrupt. So that's the general view on our problem. And for the rest of the talk, I'm going to really zoom in and tell you about a specific problem domain where we've tried to come up with methodologies towards this goal. Okay. And the specific domain we look at is a classic problem in game theory. Right? It's predicting play in normal form games. And let me just quickly remind you how these games work. Right, so what I'm showing you up here is a 2-player 3x3 normal form game. There's a row player and a column player. The row player is going to choose a row. The column player is going to choose a column. This happens simultaneously. And their choices are going to determine a specific payoff cell. The first number in that cell is the payoff to the row player. The second number in that cell is the payoff to the column player. Okay? And we can ask, and in fact many people have asked, if you know the payoff matrix that these players are seeing, can you predict the actions that they will take? Right. We look at a slightly simpler version of this. So we're going to ask, given a payoff matrix, so that's the observables that the analyst has access to, can you predict the action that is most likely to be chosen by the row player? And so by which I mean, imagine that you had many people playing this, and across these many subjects, you're going to look at all the subjects playing in the role of the row player, and you're going to try to predict the action that is most frequently chosen by subjects in that role. So there's been a large literature in economics and computer science about this problem and many different models that have been written. The oldest models thought about rationality and the implications of rationality. So Nash Equilibrium is one solution concept in that vein. More recently, behavioral game theory has come up with many alternative models that are linked a little bit more closely to psychological behaviors, right? So they actually sort of observe play and try to think about how people actually play in these games. Right? So that's been productive for another class of models. But one thing that's common about all of these models is that they're really created by the theorist who's sort of either introspecting or thinking about some stylized facts, but that theorist is coming up with a model sort of out of their head. Right, so that's a huge contrast with these machine learning algorithms, which would be directly learning a model from the data. Okay, so we're going to try to see whether we can use these machine learning algorithms to improve our prediction of play, but then going back to this first part of the talk, right, we're also going to be trying to do so in a way that's still interpretable. And let me just tell you, so we have 3 different methodologies essentially that we've tried in this paper towards that objective. The first thing we do is we take a standard black box algorithm. We use that for prediction. Okay, but we don't stop there because the output is something black box. Instead, we use that algorithm to identify cases that are well predicted by the machine learning algorithm and poorly predicted by the economic model. Right, why do we care about those cases? Well, the fact that the machine learning algorithm is predicting well suggests that there is some sort of underlying regularity there. The fact that existing models aren't predicting well suggests that that regularity isn't yet captured by the economic models. So if we can understand the regularity that's there, potentially then we can take it, import it back, and add it onto our existing models. And indeed, in our domain, that's what we're able to do. So we identify from these cases a single parameter extension to our best model, which then matches the performance of the black box. So that helps us to get a model that's actually quite predictive. In fact, actually almost too predictive. All right, so this single parameter extension that we find predicts very well. It's almost sort of a complete model of play for the data that we have. And one interpretation of that is that the model that we have is just great. It's a universal model of play. But another interpretation is that the data that we're using for training these models and these algorithms is somehow not representative of the whole space of games. Okay, in fact, all of this analysis is done on a metadata set of lab games that were designed by experimental game theorists, and they really are sort of special games in many senses. Okay, so what we took from this is, maybe we should be cautious about the models that we're learning from these games. What we actually want to do is actually obtain new instances of play in a different space of the whole sort of game space and see what's happening there. Okay. But how do you search, right? So the space of games is quite large. And so the second way in which we use machine learning in this paper is to help us identify new instances to get data for. Right? We actually use machine learning to generate instances that we think are going to break our best model, and we succeed in that. Okay, so we're able to obtain a new data set that's sort of specially optimized for our first model to fail. And then on that new set of instances, we develop a new model that actually predicts well in those instances. And the final thing we do is port together these 2 models into essentially a hybrid model or a meta model, where machine learning is actually acting at a first stage. So we're not using the algorithm anymore to directly predict play, but we use the algorithm instead to help us decide which of these 2 models to use for prediction. All right. So this is a little bit fast, but I'm going to go through each of these components in much more detail in the remainder of the talk. And one thing to point out is that none of these methods are really special to our particular domain of predicting play in games. So we're sort of excited about potential applications of these methodologies towards other problems as well. All right, so let me just dive into part 1 now. So first, let me tell you a little bit more about the data set that we begin with. So this is a data set consisting of 86 symmetric 3x3 games, much like the one I showed you earlier. Okay. This is a metadata set that was aggregated over 6 different laboratory experiments, and the original sources are listed there on the slide. Now, each of these experiments was different, so they had different experimental conditions, different subject pools, but they all shared this feature of anonymous random matching without feedback, okay, which essentially just means there's no learning. So it's two players encountering each other for the first time, playing a game that they've never seen before. For each game, we have between 40 and 147 observations. And then this data set was given to us by two computer scientists, Kevin Layton Brown and James Wright. So I mentioned earlier that there's models that have been written down for predicting play in these games. So let me just tell you about two that we're going to consider here. So the oldest solution concept is Nash Equilibrium. I assume most of you have seen this concept before, but let me just again quickly remind you. So in this game down here, A2 is a Nash equilibrium. So why? Suppose you take the other player's action as fixed. Right, let's look from the row player's perspective and fix the column player's action to be A2. Now, the row player is getting a payoff of 45 if he follows through with this equilibrium, this proposed equilibrium of A2. He can unilaterally deviate to playing A1 or A3. In those cases, his payoffs would be either 30 or 0, which are less than the payoff that he gets from playing A2. Right, so he doesn't have a profitable unilateral deviation. Okay, same thing from the column player's perspective. If we fix the row player's action to be A2, the column player can also deviate to the left or to the right, but again, that's not going to improve his payoff. Okay, so we're going to say that A2 is an equilibrium. It's sort of stable in the way that I described. So we can certainly predict Nash equilibria in these games. Sometimes there's going to be multiple Nash equilibria, and in those cases what we're going to do is we're just going to predict uniformly at random from all actions that are consistent with some Nash equilibria. So that's model one. Okay, model two is a model we took from the behavioral game theory literature. It's called the Poisson cognitive hierarchy model, and let me just briefly tell you about it. So the basic idea here is that there's players of potentially differing levels of sophistication. Okay, we're going to say that a level 0 player is a maximally unsophisticated player. That's a player who just chooses uniformly at random from their available actions. A level 1 player is going to be a slightly more sophisticated player. That's going to be a player that imagines that their opponent is a level 0 player. So your opponent is choosing uniformly at random from their available actions, and you're going to choose the action that maximizes your expected payoff given that behavior. So if we look at this game again, then each of these actions, A1, A2, A3, has an expected payoff when the column player is choosing with equal probability A1, A2, or A3. And we see that A1 yields the highest expected payoff against uniform play. So we would say that A1 is the level 1 action in this game. Okay, and then you can imagine recursively iterating to higher and higher levels, where each of these levels assumes that their opponent is has some probability of being any level that's less sophisticated than themselves. Okay, that's just a feature of the model. And then you can get for each level their best response. Okay. And in this model, they suppose that the distribution of levels in the population follows a Poisson distribution that has a single free parameter, which is this rate parameter tau. So we would estimate that parameter tau on data, and that would specify then for us a complete model which would output for any new payoff matrix a prediction for the whole distribution of play. Okay. In our case, since we're just interested in predicting the modal row player action, so the row player action most frequently chosen, we're actually not going to need this whole distribution of play, but it's going to be sufficient to give us our actual prediction, which is the mode of the distribution. Right, so if this sort of went by fast, don't worry too much about it. The one thing I actually want you to take away from this slide is the definition of level 1. That's going to be important, and we're going to be using it frequently throughout.
Both k and tau the parameters?
Just tau is the free parameter. That's right. Yeah. So tau is going to be a distribution. We think that there is a distribution over the different possible values of k, and that's going to be governed by this Poisson distribution. All right, so I hear that you've spent all the morning running predictive models, so I probably don't really need to go through what cross-validation is, but let me just quickly do this anyway. All right, so throughout all the prediction accuracies that I report for you are going to be tenfold cross-validated. So what I mean is we're going to take our data set, so all of the games, we're going to randomly split it into 10 equally sized subsets. We're going to use 9 of those subsets for training, okay, and in this case for estimating that tau. And then we're going to test the model on the yet unobserved instances in the final subset. Okay. And throughout, we're going to evaluate accuracy using the correct classification rate. So this is a very simple loss function. We're literally just going to look at the fraction of test instances where your predicted action for the row player is indeed the modal row player action for that game. And then what we're going to do as a standard is we're going to change what we take to be the test set. Okay, so we're going to choose it, yeah.
I have a quick question.
Yeah.
For the model, so just like each player has its own level, or there could be players at the same level, and when they were at the same level, like at the level playing, how are they going to compete or play with each other at the same level?
Yeah, so it's a quirk of, yeah.
Repeat the question for the people watching.
Sure, I think he was asking about what happens when 2 players have the same level. Yeah, so it's actually assumed in this model that that doesn't happen. It's assumed that, well, no, actually it could be that players have the same level, in which case they would each just play the action that was best for that level. But it's assumed that players actually think that other people are of levels that are less sophisticated than themselves. So players don't actually entertain that possibility. That's just a feature of the model. Okay. All right, good. So now we're going to change what we take to be the test set. We're going to retrain, re-estimate the values for the free parameter, predict out of sample on this new test set, again using the correct classification rate as our measure of accuracy. And we're going to do this taking every possible choice of the test set. And then finally, the reported prediction accuracy is just going to be the average prediction accuracy across all 10 possible choices of the test set. All right, so now let me show you the actual accuracies. So throughout, I'm going to present to you accuracies relative to 2 benchmarks. Okay, so one benchmark is going to be a fully naive benchmark. Right? So one thing you can always do in this problem is just guess at random. If you do that, you're going to correctly classify the actual modal action 1/3 of the time. Okay, so that's the first accuracy you see there. And then at another extreme, you could imagine the prediction that you would get if you actually had observation of the test data. In that case, you should be able to get a perfect prediction. Right? So if you actually see many instances of play in a given game, with sufficient data, you're going to be converging to a correct prediction of the mode. Right? And we can normalize the naive benchmark to sort of 0% completeness, and the ideal prediction benchmark to 100% completeness. And I'll also show you these accuracies relative to sort of renormalized from that perspective. All right, so here's how our models do. Okay, the uniform Nash model correctly classifies the modal action 42% of the time. And the Poisson cognitive hierarchy model that I showed you does actually much better, and it correctly classifies the modal action 72% of the time. All right, so both models are clearly predictive, and this PCHM model is very predictive. So one note about the PCHM model, it turns out that when you estimate tau on the training data, the model actually reduces to just prediction of the level 1 action. Right, so this is why I told you can sort of ignore actually most of what's on this slide. If you predict the PCHM prediction, that's actually, for every game, the same prediction as if you just assumed everybody was playing as if they're level 1. Okay, since that's a much simpler model, we're just going to work with level 1 from here on out instead of the full PCHM. So that's great, it's at 72%, but it's not fully complete. So now let's see how machine learning does, right? And we can take essentially a cut and dry machine learning approach here. What we're going to do is we're going to identify each game with a vector of features that are relevant to the strategic properties of those actions, all right, of the game. So some example features are as follows. For each action, we define a feature for whether that action is part of a pure strategy Nash equilibrium. Okay, we define a feature for whether it's part of what's called a Pareto-dominant Nash equilibrium. Okay, so that's sort of a very good Nash equilibrium where the payoffs for both players are higher than, I'm being a little bit loose here, but just think about it as the payoffs to both players are weakly higher than the payoffs in any other pure strategy, Nash equilibrium, and moreover, for one player, it's strictly higher. Okay, so just think about it as a Nash equilibrium where the payoffs to both players are really good. Okay, so we have a feature for that. And additionally, we have features for these level K properties that I described previously. So we'll ask, is that action level 1? Is it level 2? So forth. And another feature, this is sort of capturing potentially altruism. So is the action part of an action profile that maximizes the sum of player payoffs? Okay, this is not the complete list. And then what we do is we train a decision tree ensemble to predict the modal role player action given access to these features. So now let's return to the accuracy table. And what we see is that the decision tree ensemble improves upon the level 1 model. Okay, so now we're getting to 77% accuracy. Right, so it's improving, but we don't really know why it's improving upon the level 1 model. So then the next question we can ask is sort of what is the gain here? And to do that, what we do is we focus on the games where the decision tree ensemble is correctly predicting the modal action, but the level 1 model is not. Okay, there's 14 games that have that property. And so as I suggested earlier, these 14 games are sort of interesting because there's certainly some sort of pattern there that the decision tree ensemble is picking up on, but the pattern is not level 1 play. So by the way, so I don't know whether you were working with decision trees ensembles today. Don't worry too much about the specific algorithm. If you are sort of familiar with decision trees, essentially what it is it's growing many different decision trees based off of bootstrapped data sets and sort of taking a vote across the trees. Okay, but this is a rather uninterpretable output. All right. So here it's an example game with that feature that the modal action is correctly predicted by the algorithm, but incorrectly predicted by level 1. And what we see is that A1 is a level 1 action. Remember, it has the highest expected payoff against uniform play. But there's another action here, A2, which yields almost as high an expected payoff against uniform play. So we'll compare 50 versus 51.6. And moreover, the potential payoffs that the role player might get exhibit significantly lower variation. Is that a question?
Yeah. I'm kind of lost with what the strategy of the game is.
Okay.
I know that you've been talking about this for a while, but it would be helpful if you would explain like what the strategy for the row column is and what the strategy for the column player is.
Yeah, definitely.
And what's winning and what's not winning, because I'm just...
Yeah, okay. No, thank you very much for this question, because this is certainly extremely important. Okay, good. Okay, so let me just explain the game again from the beginning, if that would be all right. Okay, great. So it's a simple game. Okay, it's you and another player, so the guy next to you, all right? And you can just think about the payoffs as dollars, if you will. Okay, that's not quite precise, but just take it to be yeah, exactly in dollar units. All right. You're the row player.
So does that mean that like I'm like this?
That's right, yeah. So you're going to pick either A1, A2, or A3, each index to a row.
Okay.
All right, yeah, it's a little bit confusing because they're labeled the same way, all right? But you pick the row.
Okay.
Right. He's going to pick the column. Depending on the choices that you guys make, there's going to be some cell that we're going to select. Right? So for example, if you choose A1 and he chooses A1, then the cell we're selecting is 25, 25. So think about that as you walk out with $25, he walks out with $25. Okay? Yeah, and so now you see the sort of the rules of the game, right? So you're going to simultaneously choose these. You can't talk. Right? You can't coordinate. It's not like you're going to see his action before you take your action. Think about it. You're in separate rooms. You write down your action on some slip of paper. I aggregate your slips of paper and then tell you how much money you've won. All right, so what do you want to pick in this game? You don't have to. 45. What? Yeah, no. So the what's difficult here? Right. No, but so what's interesting here, right, is that you don't get to choose his action. You can't choose A2, A2. Okay, so you could choose A2. So that would be a reasonable answer, right? And A2 would be best for you if you chose A3. Yeah, so actually, so why do you want to choose A2? Actually, I'm kind of curious now. All right, so these numbers are these colors are colors that I've added. The subjects don't see that.
You know, like the 45, but I wouldn't know what his options are, so yeah, I know it's also in the center.
Yeah.
I'm a level 0.
No, you're not a level 0 because a level 0 would be choosing uniformly at random. So you would be saying they're all the same to me. Just flip, like essentially generate a A1, A2, or A3 with equal probability. That's what a level 0 player would do. You actually have a preference, right? You liked A2. Okay. No, but there's sort of many different ways one might think about predicting how you would have chosen, right? And essentially the level 1 action is saying, just look at the possible payoffs you could get, right? If you choose A1, you're either going to get 25, 30, or 100, depending on what he does. Okay. Let's just add those numbers up for each row. And let's predict that players choose the action that has the highest row sum. Okay, that's going to be equivalent to how I described it earlier, which is the highest expected action when the other player is randomizing with equal probability. All right? So I mean, that's kind of a reasonable way to look at it too, right? Okay. Yeah. Both players always choose A3. Interesting. Why is that? So sorry, I wasn't sure if you said that. The first number goes to the row player. The second number goes to the column player. Okay, good. So that's also an important clarification. The first number to row player, second number to the column player.
Right? Because then it's either 165.40 or 30.45.0 or 25.40.0. Of course, I'll choose.
Yeah. So that's the 165.40.
Okay, so I was like, why would anybody ever choose A1?
Yeah, okay, great. So this is also an important clarification.
Okay.
So if you choose A3, the possible payoffs you might get are 31, 0, and 40.
Okay.
And that's actually not really an attractive action.
Okay.
Yeah.
One more clarification. So did the players have this table before they play?
That's right. So you see the whole table. You see the payoffs to the other person as well as the payoffs to yourself.
So I'm trying to win just without any sense of what they might do. So
Exactly.
either
You might have some model of what they're going to do or some belief over how they're going to play. Yeah.
Oh, so hence the whole like cognitive thing about like, am I maximizing myself? What am I thinking they're going to do? That's all the sort of internal stuff you're trying to
that's
model, right?
That's exactly. You might include that in your model. Yeah. Okay, this is really exciting. I thought I was going to be talking about machine learning, but I get to actually also explain game theory. So, yeah. All right. Great. Okay. So in this game, again, the level 1 model, which is sort of one reasonable way of predicting play, is to say add up the possible payoffs that you get for each action and just predict the action that corresponds to the highest row sum. Yeah.
Could you improve the model by adding the rule of the variance of the row?
Great. Okay, so that's exactly where we're going, okay? She wanted to sort of include variance of the payoffs, okay? Yeah, so that's exactly where we're heading. All right. So what I've shown you here is not the row sum. It's the row sum divided by 3 because we're thinking about it as the other player is choosing either A1 or A2 or A3, each with probability 1/3, and we're finding the expected payoff against that strategy. But what we see is that A1 is indeed the level 1 action. It has the highest expected payoff against uniform, okay, equivalently the highest row sum. But A2 has almost as high a row sum. Right, so if you sum up 40, 45, 65, that's almost as high as what you would get for A1. And moreover, the possible payoffs that you can get by choosing A2 exhibit significantly smaller variation. In this game, what we see is that although the level 1 action is A1, the action A2 is played much more frequently. Now, if you show this to an economist, this kind of behavior looks very familiar. It basically looks just like risk aversion, right? You don't like variation. All right, So we can take that very familiar output, that regularity, and also, by the way, so this is not just happening in this game, it's actually happening in all 14 games where behavior is correctly predicted by the algorithm and incorrectly predicted by the level 1 model. So now it looks like people are risk averse. We can take that level 1 model and we can modify it in a very simple way to accommodate risk aversion. Okay, specifically, what we're going to suppose is that instead of directly receiving the payoff that's in the matrix, what they receive is that payoff raised to an exponent alpha. And then when alpha is less than 1, they're essentially going to be risk averse. So this is a single parameter extension to the level 1 model, and it's quite interpretable. And what do we find? What we find is that this level 1 alpha model actually predicts better than the decision tree ensemble. Right, I mean, I don't want to be too strict on better because we have these standard errors, but it at least performs as well. Okay? And what we take away from this is that we don't have to take the black box necessarily as the end output. The black box can actually, in some cases, lead us towards interpretable parametric models that predict as well. All right, so that's sort of the conclusion of part 1 of the paper. And we could just stop here and say, look, we have this level 1 alpha model. This is great. It's predicting correctly in 79% of instances. Right, that almost looks like a universal model of play. So we're done. Right. The catch is that the data set that we began with, these 86 lab games, those are rather special games. Right? So how did we come up with this payoff matrix? Well, somebody wrote that down. Right? And you typically don't want to write down arbitrary payoff matrices. You want to write down something that you think is going to generate interesting insights. So we might be suspicious of the findings that we're getting when we're training on this very special data set. And so in particular, we might wonder, is the performance of level 1 alpha due to idiosyncratic features of the lab games? Right? It could be that people are especially writing down games in order to make level 1 a good model of play. And we might also wonder what regularities exist beyond level 1 alpha. So is that a question?
How do you decide the value of alpha? Do you have
Oh, great, yeah. So alpha we take as a free parameter, and we estimate that on the training data. So we treat it like we were treating tau previously, right? So we have this training data. Right, those 9 subsets, we find the value of alpha that best fits behavior in those 9 subsets, but then we evaluate the model out of sample. Okay, great. So to answer these questions, we sort of can't return to our original data set, which we've exhausted. We actually need observations of play in new games, new kinds of games. Okay, so that's going to be part 2. And the first thing we actually tried was just randomly generating new games, right? It's sort of a natural thing to do. We had these lab games that were special, hand-designed. Let's create new payoff matrices where we're just going to sample payoffs at random from some distribution. So we did that, and we created a new data set of 200 3x3 games. We went on Mechanical Turk, had a bunch of people play these new games. And what we found is that on these new games that were randomly generated, again, not specially designed to make level 1 go, the level 1 and the level 1 alpha models actually perform better than they did on the lab data set. So the level 1 is actually now predicting correctly 87% of the time. Level 1 alpha is predicting correctly 92% of the time. So what happened there? It turns out that when you randomly generate payoff matrices, you actually generate games that are sort of strategically simple, where there is actually an obvious answer to pick, and that answer often happens to be level 1. Right, so I won't bore you with too many of the details here. We essentially use 2 different measures for strategic complexity of the game. So one measure we looked at is the number of pure strategy Nash equilibria, okay, where if you think about Nash equilibria as sort of appealing or reasonable action profiles to go for, the more there are, in some sense, the more complex the game is. Another measure we used is the number of rationalizable actions. If you haven't seen that term before, don't worry too much about it. It's another way of defining what a rational player should go for. And what we see is that in these randomly generated games, there tend to be fewer pure strategy Nash equilibria. So the distributions here, the blue bars correspond to the lab games, the green bars correspond to the randomly generated games. And you see that the blue bars have more mass on the higher numbers. Yeah.
How do you account for the possibility that the people at enter are more risk averse?
are more risk averse. So it's not necessarily, right? So risk aversion would make level 1 alpha potentially a better model relative to level 1. Right? But it wouldn't necessarily mean that level 1 is actually a better model. But you are getting to something important, which is that it could be that what we're seeing is driven by subject pool differences. Right? Previously so we're sort of varying two things simultaneously, right? We're going from the lab games to these randomly generated games, but we're also going from lab subjects to mechanical Turk subjects. Okay, so what we actually did is, this I'm not showing here, but we actually reran the lab games with mechanical Turk subjects. And so what I can tell you is that what we're seeing is not entirely due to the subject pool. The game structures are an important factor in these performances.
When you render
Yeah.
payoffs, the ranges are still the same, right?
The range is still the same, yeah. So we generated the payoffs uniformly from 10 through 90, just to keep it consistent with the lab games. All right, great. So, the random games turned out to be more conducive to level 1 play. So, on the one hand, that's sort of reassuring because it tells us that our previous results for the level 1 and level 1 alpha model somehow weren't that idiosyncratic to the special features of the lab games. But on the other hand, it means that these games are actually not that helpful for identifying new regularities besides the level 1 alpha and level 1 model because, again, these are almost complete models of play. So if we want to somehow explore this space of games and find a new subset of games where the level 1 alpha model isn't doing that well, we need a more sophisticated game generation procedure. Right. Now, one way we could have done that is mimic the experimental economists and sit down and handcraft games where we thought that these games were strategically interesting and potentially not conducive to level 1 play. And instead, we chose to algorithmically generate those games. So let me tell you a bit more about how exactly we did that. Right. So at a very high level, the first thing we did is we trained an algorithm to predict the frequency of level 1 play based on the payoff matrix. With that in hand, we were then able to, again, randomly generate games, but now oversampling from those games with a predicted low frequency for level 1 play. Okay, let me give you more details now. So first, we're going to build these algorithms on features of the game. So let me tell you a bit about some of the features that we ended up using. One example feature is the level 1 action itself part of a pure strategy Nash equilibrium? So in this game that I'm showing you up here, A2 is the level 1 action. It has the highest row sum. It actually is part of a pure strategy Nash equilibrium because A2 is a Nash equilibrium. So you can verify for yourself, if you're the row player and you know that the other player is choosing A2, then choosing A2 is a best reply for you, right? So there's nothing you could choose that would yield a higher payoff because A2 gives you 20 and that's the best thing that you could get. Again, fixing the other player's action to be A2. Right, and same thing for the calm player if you flip it. So our answer for this feature would be yes, in this game, the level 1 action is indeed part of a pure strategy Nash equilibrium. Okay. Another feature we look at is a difference in the sum of row player payoffs if you choose a level 1 action versus if you choose a next best action. So again, in this game, level 1 action is A2. That gives you a row sum of 150. We can now look at the action that gives you the next highest row sum. That would be A3. That gives you a row sum of 130. Well, here the gap is 20. Okay, so that's one sort of measure of how level 1, how much better is the level 1 action relative to its nearest competitor. These are all features that essentially capture different ways of measuring how appealing the level 1 action is. Another feature that we'd include is whether the game contains a Nash equilibrium that yields high payoffs for both players and is not itself level 1. In this game, yes. So if you look at the action profile A3, so here both players are getting a payoff of 100, so that looks really good. But that action profile does not, in fact, include the level 1 action A2. So we defined many features like this. Given these features, we then again used a decision tree ensemble to learn a map from these various payoff matrices into a prediction for the frequency of level 1 play. Right, so we took as our data set all of the observed play on the lab games as well as all observed play on the randomly generated games. For those games, we know ground truth, right? We know, in fact, the true distribution of play in these experiments. So we know the frequency of level 1 play in those games. And so now we're turning it a bit, right? Previously, we were using the algorithm to predict the action that was played. Now we're using the algorithm to predict the frequency of level 1 play. So maybe, and these are not the true numbers, but potentially in that first payoff matrix, 73% of people chose the level 1 action. In the second payoff matrix, 65% of people chose the level 1 action, so forth. Yeah?
Does the presence of zeros have an effect on like people's strategies?
Yeah, so
Like, the second one has like more zeros than the top one.
mhm.
Like just the presence of zeros makes me anxious.
Uh-huh.
Like, and I'm not even playing the game.
Yeah, we really should have consulted you before defining these features. So we actually have a feature. I don't remember whether it's for zeros or 100s, but we have a feature for one of those extremes. Yeah. Okay. All right. So we have this map now, right? Okay, so this is clear. So it's a map. It takes as input the payoff matrix, and it outputs a prediction for what fraction of your subject pool is going to end up choosing the level 1 action. And then given that algorithm, we can now again randomly generate new payoff matrices. And now for each of these new payoff matrices, remember, we don't have observed play for these new payoff matrices, we can nevertheless use the algorithm to predict the frequency of level 1 play in those games. Okay, we don't know if that's correct, but we can certainly make these predictions. And what we chose a rather arbitrary cutoff. We just decided more than 50% is a lot of play and less than 50% is sort of not that much play. And for each of these randomly generated games, we just got rid of those games where the predicted frequency of level 1 play exceeded 50%. Right, so here, potentially for the second game, we predict 56%, so let's just X that out. And let's repopulate that with a new randomly generated game. Again, apply our algorithm to predict the frequency of level 1 play. Okay, here, if it's lower than 50%, that's good, we'll keep it. And iterating this procedure, we can eventually end up with a data set where every single game is predicted to have low frequency of level 1 play. It turns out that these games that we algorithmically designed in this way end up being strategically interesting by the two measures that I showed you previously. So again, this wasn't by design, right? We didn't tell the algorithm, generate strategically interesting games. It just turned out that in trying to create games where level 1 play was low, the algorithm decided to generate strategically complex games. So here, let's see, the blue bars correspond to the randomly generated games. The green bars correspond to the lab games. The yellow bars correspond to our algorithmically designed games. And again, we have these two measures of complexity. So think about it as bigger numbers correspond to more complex. And what you see is that as we go from the randomly generated games to the lab games to the algorithmically designed games, we're shifting mass to the right. So in essence, we're producing data sets or sets of, it's not exactly a data set, we're producing sets of games that are more strategically complex by these measures. Okay. All right. So here are the, yeah?
I just wonder, is there something about the fact that the games are symmetric that makes them more complex?
So that's a great question. So most of our analysis, her question is about symmetry in the games, right? So what she's noticed is that most of the games that I've shown you are symmetric games. Indeed, we almost exclusively focus on symmetric games just to keep the setting, again, simple. The randomly generated games actually weren't asymmetric, but the algorithmically designed games were, by design, symmetric games. So right, so you could think about asymmetry as creating yet a different kind of complexity. Yeah, we didn't measure it like that. That's sort of an interesting question. Okay, great. So now here are the predictive accuracies of the existing approaches, right, the different approaches that we've looked at so far, for this new data set of algorithmically designed games. So again, we collected play on mechanical Turk. And what we see is that now the performance of the level 1 model and the level 1 alpha model plummet. So the level 1 model is predicting correctly 36% of the time, and the level 1 alpha model predicts correctly 41% of the time. Okay, remember the previous prediction accuracies were like between 70 and 90%. So what this tells us is that the algorithmically designed games succeed in being poor matches for this level 1 model. Okay. But notice that the decision tree ensemble is still actually doing really well. Right? It's getting us a prediction accuracy of 73%. So it's not that these games are fundamentally unpredictable. There is some sort of regularity there. It's just that that regularity is not captured by the level 1 model and the level 1 alpha model. Okay. So that's good now, because now, again, if we're trying to identify something beyond those models, this data set is promising for that identification. All right. Now, this decision tree ensemble is essentially non-interpretable. You don't want to see it. But one way of getting at what it's doing is to look at a very constrained version of the ensemble. Right? So basically constrained to the extreme. So we're going to look at a single decision tree. So instead of voting across many decision trees, we're going to look at just one. And furthermore, we're going to constrain this decision tree to be extremely simple in the sense of being very short. Okay, so I'm actually going to show you that decision tree, and it turns out to be very interpretable. Okay, so the decision tree goes like this. There's a first node, and at that node it asks, is action A1 part of a Pareto-dominant Nash equilibrium? Okay, remember the Pareto-dominant Nash equilibrium is a Nash equilibrium where the payoffs to both players are quite high relative to the other Nash equilibria. If the answer is yes, then we predict action A1. If the answer is no, then the tree asks, is action A2 part of a Pareto-dominant Nash equilibrium? If the answer is yes, we predict A2. If not, we predict A3. So essentially, it looks like this tree is asking us to predict actions that are consistent with Pareto-dominant Nash equilibrium. That's something we can all understand. One thing we might not like about this tree is the specific ordering of A1, A2, and A3. So what we did is we instead wrote down this very related model, which we called Pareto-dominant Nash, where we find all actions that are consistent with this notion, Pareto-dominant Nash equilibrium, and we predict uniformly at random from those actions. So here are the prediction accuracies that I showed you earlier, and here's the performance of the Pareto-dominant Nash equilibrium model that I just described. Okay, so this does very well, actually, right? It predicts correctly 65% of the time. It's not as good as the decision tree ensemble, which we would expect because we've really artificially constrained it significantly. But what's sort of surprising is that despite those constraints, it actually ends up to be rather good. It's still a huge improvement over the level 1 models. So again, we could stop here and say, look, now what we've learned is that the Pareto-dominant Nash equilibrium model is really good. In fact, much better than the level 1 models. But that would be a misleading conclusion because we're looking now at a very special data set. Again, this is the special data set of games that we algorithmically designed. Right? Is that data set somehow better or more representative than the lab games? It's hard to say. So one thing we can do is we can actually aggregate all of the different games that we have. So the lab games, the randomly generated games, and then these new algorithmically generated games, and evaluate how well these models do on this whole aggregated data set. And when we do that, we see that the PD&E model, this Pareto-dominant Nash model that performed so well just now, actually underperforms the level 1 model. Right, so here the level 1 models are getting to sort of 63, 68% accuracy. PD&E is at 56% accuracy. Right, the decision tree ensemble is still the best at 74%. And by showing you this, I'm not trying to suggest that now we've learned that the level 1 model is in fact better than the PD&E model. Really, in some sense, these two tables are meant to illustrate that we should exhibit a lot of caution when we're trying to rank models, right? Because the ranking of the models is going to be particularly dependent to the data generating process that you have. And unless you're pretty confident that you have access to the representative data generating process, sort of the most interesting or meaningful one, then you should be a little bit careful. All right, so now the level 1 models and PD&E model both do all right, not that amazing. The decision tree ensemble is still doing quite well. That may suggest that there are regularities beyond PD&E and level 1 that we haven't yet discovered. Another possibility is that these two models essentially cover the whole space, It's just that they're predictive of different models. They're predictive of play in different games. And a simple way of seeing that, some evidence towards that, is by looking at how often these games predict correctly on the same, how often these models predict correctly on the same game. So what we've done here is taken the 486 games in our aggregated data set, and for each game asked, does PD&E yield the correct model, the correct prediction of play? And does the level 1 alpha model yield the correct prediction of play? And what you see is that there is 155 games where both models give you the correct prediction. There is 41 games in which both models give you the wrong prediction. But what's interesting is that there's this very strong off-diagonal. Right? So there's 115 games, for example, where PD&E predicts correctly while the level 1 alpha model predicts incorrectly. Right? So that then is suggestive that indeed these two models might apply to different kinds of games, which then points to a potential gain if we can learn when one model is a good model of play over the other one. Now, what's a little tricky about this is that we can't decide this ex post, right? We can't evaluate the two models and see that the level 1 model predicts correctly over the PD&E and therefore use the level 1 model. We have to somehow decide which model to use for prediction based on no new information about play, based on exactly just the primitives of the payoff matrix itself. Right, so how do we do that? And our answer is to use machine learning to help with that model selection task. All right, so before I get into the final part of this talk, are there any questions about anything we've looked at so far? All right. Okay, so let me tell you about how we try to do this. All right, so our approach is to use machine learning to choose between these two models, level 1 alpha and PD&E, game by game. So there's a couple of literatures that this is very related to. So the mixture of experts literature, model trees, forced cast combinations. Okay, and essentially, there's many different ways of sort of choosing between models. The specific approach that we use is the following. So first, we take the training data. Okay, for the training data, you know ground truth, right? You know the true distribution of play for each of the games, so you know, in fact, how well these models are performing. And what we can do is we can go game by game and ask, did the model predict correctly for this game? Okay, what that's going to give you is a binary error vector, right? So it's going to tell you for this game, let's say model A predicted correctly, model B predicted incorrectly. Okay, for game 2, both models predicted correctly, so forth. And we can fit a decision tree to predict for each game the probability that a given model, okay, so either level 1 alpha or PD&E, is going to predict the correct modal action. Right, so this is a little bit different from some things we've done before because we're going to predict here a probability instead of a binary outcome. Right, so what the tree would say is, look, given this payoff matrix, I think there is a 72% chance that level 1 alpha is going to give you the correct prediction. There is a 23% chance that PD&E is going to give you the correct answer. Okay. And then for a new game, what we can do is we can take the features corresponding to that game. We can run those features through our decision trees here and yield a prediction of the probability that each model is going to be accurate. Then what we can do is we can simply go with the model that has a higher predicted accuracy and use that model for prediction of play. Right, so for this payoff matrix, it was 73% accurate prediction of accuracy for level 1 alpha, 23 for PD&E. Well, then let's go with level 1 alpha and let's use its prediction.
And those probabilities are independent of one another, correct?
What do you mean by independent?
Sorry.
Oh, yes, that's right. Yeah. So we built a different decision tree for each model. Right. So I guess technically you could have used a decision tree to predict the two jointly. Yeah. So we didn't.
And so what types of features is the model taking into consideration to figure out what, like, if it should be this, we should use this predictive model versus this other predictive model?
Yeah, so that's a great question. So we use the same feature set that I described earlier. So I only give you a few example features, but basically these are all features describing various strategic properties of the game that we thought might be relevant.
Okay, so like if both people can
Yeah, exactly. Okay, yeah, great. We also included some features that didn't directly reference level 1, like how many pure strategy Nash equilibria are in the game, okay, things like that. Yeah, great. No, but these features are all handcrafted by us, right? So it's also sort of an interesting question of what features you might sort of generate you can automate the feature generation process. I'll sort of talk about that briefly at the end. Okay, but here we used direct domain knowledge. Okay, great. So then for each new game, we can use the algorithm to direct us towards either predicting using model A or predicting using model B. And this hybrid model, which combines level 1 alpha and PD&E, turns out to vastly outperform both component models on our aggregated data set. Right, so level 1 alpha, again, was 68% accurate, PD&E 56%, and this hybrid model is getting us to 79% accuracy. Again, remember, this is all out of sample, right? That's really important, because if we're just looking at in-sample, then certainly the hybrid model should outperform both components. It's a more complex model. It literally nests the two models. But this is out of sample, where it's not guaranteed that the additional complexity is going to yield improvements at all, not to mention improvements of this size. Yeah?
Can you remind us what level 1 alpha means as a strategy? I got the level 1 is random.
Yeah. So level 1 alpha, thank you. Level 1 alpha is the extension that we created in part 1 of this exercise, where we discovered that players behaved as if they were risk averse. So we included this alpha parameter to capture risk aversion, and but otherwise it's the level 1 model. Okay. Yeah. Right. So one more reassuring thing, by the way, is that in fact level 1 alpha does outperform level 1 in these new data sets as well. Right. So in some sense, that's a true out of sample test that this parameter extension is meaningful. Great. All right, so the hybrid model is improving predictive performance. And one thing we might be curious about is how exactly this model assignment is working, right? So which games are being sent towards the level 1 alpha model, which games are being sent towards PD&E. And here we were sort of lucky that when we were building these decision trees that predict the probability of accuracy, these decision trees ended up being actually quite simple. So low numbers of splits actually yielded the highest cross-validated error. And what that means is that actually we were able to piece together a tree that describes the model assignment, which is not too unfortunate to look at. Okay, it's still, this is not my ideal still for interpretability, but it's at least something we can say a few things about. All right, so roughly what's going on is the model assignment tree. Okay, so let me just be clear about what this is. Right, so what the tree does is there's different nodes with different features, and we ask questions about these features, and then based on where we end up, we're going to choose either PD&E or level 1 alpha as our model that we're going to use for prediction. And you see that there's 4 different terminal nodes here. So roughly, we're taking the space of all payoff matrices, and we're partitioning the space into 4 classes. 2 of those classes are being sent to PD&E, and 2 of those classes are being sent to our other model, level 1 alpha. And by reading off which features, which combinations of features lead you to these different classes, we can sort of understand a little bit of how we're doing the model assignment. And there are some of these classes where sort of correctly classifying the model is not actually a big deal. So I don't know how well you can see this, but the first box that we have here, the one all the way on the right, so those are games that are being sent to PD&E. But if you look at the actual accuracies of using either model for predicting play in those games, both models really do very well. So level 1 alpha gets you the correct answer 89% of the time. PD&E gets you the correct answer 94% of the time. So yeah, it's better to send those models to PD&E, but we're not really achieving a substantial improvement by choosing the better of the 2 models. In contrast, if you look at the second box here, so second box from the left, that's 116 games that we're sending to the PD&E model. And for those games, the accuracy of the level 1 model is just 22%, while the accuracy of the PD&E model is 72%. So that's a class of games where correctly choosing which model to use yields significant improvements. So now we can sort of ask, what are the games that are being sent to that branch, that terminal node? And those turn out to be games where there is a very good Nash equilibrium. And by very good, I mean it's Pareto dominant, it's symmetric, and it moreover yields the maximal payoffs for both players. okay, by which I mean in those Nash equilibria, you get the largest number you possibly could in the whole payoff matrix. Okay. And moreover, that level 1 action, that Nash equilibrium does not include the level 1 action. So one example game with that property is this one that I'm showing you here. So it turns out that action A2 is the level 1 action. It's also level 1 alpha for the estimated alpha parameter. But if you sort of stare at this payoff matrix, right, I'll just give you a moment to look at it and think for yourself what you would like to choose. Okay, so would you really choose A2? So it turns out that many of our subjects don't. They like A1. And one reason for this is potentially just that A1 looks really good. So our machine learning algorithm looks at this game and decides we don't want to use level 1 as our model for predicting play in this game. We want to use PD&E instead. And indeed, if A1 is this Pareto dominant Nash, so the PD&E model would predict A1 for this game. All right. So this basic structure that we used, we decided to take model A to be level 1 alpha and model B to be PD&E. But there's nothing about the hybrid model that's specific to those two component models. So in principle, we could imagine building hybrid models using different component models of play. So we didn't explore that too much here, but some alternative possibilities. Of course, we could take 2 different behavioral models or 2 different economic models. But some other exciting things one might do are combined, let's say, a behavioral economic model as one component model with a more traditional, let's say, algorithmic model, such as lasso or logistic regression. Right? So you might imagine, yeah.
Maybe it's a bit out of the box, but another parameter that could help you identify the strategy of the players would be the time they take to answer. Like, I guess
Mm-hmm.
in your mechanical Turk exercise, you have this time before answer. And
Yeah.
this could be determinant in the easy answer. I know one of the answers related to the
Yeah. So that's an interesting idea. So I would see that as falling in our second bullet here, right? So sort of these traditional models predict play based off of the game matrix itself. But you can imagine using a different model that takes into account some of these more non-traditional data sources, such as response times. The people have done work on eye tracking or things like this. Actually, we also explored, it didn't end up in the final paper, but we also explored using crowd predictions, right? So you can imagine asking people to predict how other people will play. And those are all non-traditional models of play, and you could imagine building a hybrid model that tells you, for this game, you want to use the response rates. For this game, just go with Nash equilibrium. Right? So that would be one potential hybrid model. In the first bullet point, I was thinking more about combining interpretable behavioral economic models with something like logistic regression. Right? And one thing I find interesting about that possibility is our hybrid models are already blurring this distinction between behavioral and algorithmic approaches. Right? So there's this sort of naive categorization, one might say, where you can say some models are statistical, some models are economic. I'm not exactly sure that distinction has meaning, but to the extent that distinction does have meaning, these hybrid models are trying to blur that. And if you build this hybrid model, already we were trying to blur that, right? Because here, at the terminal nodes, ultimately we're using an economic model to predict play, but we're using an algorithm to decide which economic model to use. So that's already blurring it. And then if we take model A to be economic and model B to be statistical, then again, I really wouldn't know how to categorize the corresponding, the model that you're getting out of this. All right, so I'll just conclude with some discussion points. All right, so one thing that we learned from all of this was really to be cautious about how to interpret findings given specific game generation processes. All right, so I spoke a little bit about this, but let me go into more detail now. So actually, let me begin with the second bullet point. It's a little bit easier to talk about. So ranking of models. So one traditional exercise in the literature has been horse races, right? People really like asking, is model A a better model of play or model B? And then what you can do is you can run an experiment, get play, analyze these two models, and find which one ends up predicting correctly more frequently. And what we find in our analysis, given that we have these three very different data sets of games, we find that the ranking of these different models, level 1 alpha, PD&E, really depends on what game generation process we're considering. So if you're looking at lab games, level 1 is much better than PD&E. If you're looking at the algorithmically designed games, then PD&E is much better than level 1. So I'm personally a little bit skeptical about the meaningfulness of these performance rankings, given its explicit dependence on the data sets that you're looking at. And our hybrid models really actually try to step away from the goal of having a horse race, because essentially what the hybrid models say is we don't have to have a verdict on one model being better than the other model. It can very well be that one model is better some of the time and the other model is better in other instances. And actually that represents an opportunity, because then if we can figure out when one model is better, when the other model is better, we can actually potentially improve on both. Okay, so that's sort of the philosophy behind these hybrid models. Yeah?
If you were to have found that in your three different data sets that perhaps there were three different models that were performing well, can the hybrid framework that you set up incorporate a decision between three types of models?
Yeah, absolutely. Great. Okay, so I'm glad you asked that, because actually I meant to say that. Right, so there's nothing about the hybrid model that's specific to the two component models we looked at. That's nothing about it that's special really to two models. Right, now, at some point in time, if you have too many models, then I'm not sure we can call that interpretable anymore. But certainly at the level of 3, we could just repeat the exercise that we did. Right, so what we would do is we would take the training data, build a decision tree for each of these 3 different models for predicting whether that model will predict play accurately. And the hybrid model would use the algorithm to choose between the 3. Great. Okay, this first bullet point, it's a little bit more complicated to say what I mean here. But another way in which the game generation process is important is the following. So take our initial set of lab games, right? That was a relatively small number of games. We had 86 games. And those 86 games were maybe strategically similar, okay, in their game structures. When you're looking at a data set like that, right, that's going to actually produce an advantage for simple, low parameter models, because you don't have that many kinds of games, really. Right? So in those instances, if you actually try to build a very complex model, there's a potential for overfitting. As we increase the diversity of the data set of games that we're considering, so as we throw in these randomly generated games and also these algorithmically generated games, now suddenly, more complex models might actually yield a real improvement in prediction, exactly because we want to take into account the diversity of the underlying instances. So one sort of takeaway from this is that we're talking about the ideal complexity of the model. That's also really dependent on the game generation process that you have in mind. So it's also sort of hard to just say objectively, the ideal model has this number of parameters. It's again, for predicting what kinds of settings, how diverse are your test instances. All right, and then some opportunities. So going beyond what we've done here, right, we focused exclusively in this paper on categorizing games. So we were really focused on the existence of heterogeneity across the different games and the corresponding potential for different models to do better for different games. But you might also think that there is a similar sort of heterogeneity across subjects. Right? Maybe some subjects play like they're level 1 alpha, and different subjects play like they're Nash Equilibrium people. In that case, we might actually imagine building a hybrid model where the algorithm doesn't choose which model to use for which game, but chooses which model to use for which person. And that's something we really didn't explore here at all, but I certainly think that similar methodologies can be applied to that problem as well. Okay. And then a final comment. All right, so here, there was a question earlier about which features we used, and I mentioned that we handcrafted all of the features. So we used domain knowledge to decide which properties of the payoff matrices might be strategically relevant. You could also imagine using an algorithm to automate those features that you begin with. And there's this paper by Hartford, Leighton Brown, and Wright, which essentially tries this. So they take a deep learning approach. So their direct input is the payoff matrix itself. They don't go through the second processing of developing handcrafted features based on that payoff matrix. And so I think it's a very interesting paper. The catch there is that the features that they get from that process aren't necessarily themselves interpretable. Right, so sort of the gold standard would be to have an automated process that yielded interpretable features that you can then use for prediction. But at present, at least I don't know of any successful implementations of that in this domain, and my sense is that it's hard in general. All right, so then, speaking of which, let me briefly talk about some of the related literature. So in our domain of predicting play in games, there's been some fantastic work by Kevin Leighton Brown and James Wright, who are computer scientists. So they have a paper where they try to improve this PCHM model that I showed you at the beginning of the talk. Remember, level 0 was this maximally unsophisticated player, and we decided that the level 0 player was going to randomize uniformly at random over their actions. And from the seed, we then recursively defined the more sophisticated levels. And they consider replacing that level 0 specification with an algorithm. Okay, so that's also really in this vein of using machine learning as a complement to theory building. And then they also have this deep learning paper that I mentioned. And in a different setting, so this is predicting choices that people make between various, we call them lotteries. So essentially it's choices that you make that have uncertain outcomes. There's also been some work on using behavioral neural networks to make predictions, again, where the goal is to have this neural network somehow build on or mimic the properties of the existing underlying economic theories. And then in terms of general methodology, there's been some work by econometricians and IO economists where people have tried to sort of regularize towards a theory, right? So you can think about the machine learning algorithm as this maximally unrestricted search in the domain, and the theory as being a very specific choice. So again, going back to our initial slides with these prediction rules, right? And how much we want to constrain the function. You can think about the theory as imposing a lot of structure on the function, the machine learning algorithm as not imposing nearly as much. And there's been some work on running these algorithms, but in a way that we sort of try to bias towards the existing theory. Okay, so happy to talk about any of these other papers offline with more details. And then just to conclude, and then we can have some questions at the end. So what we've tried to do in this paper is to show that we could use machine learning not just to develop better predictions, but also potentially to help us improve our understanding of a given problem domain and to develop simple and portable improvements on existing models. So we've shown you 3 different methodologies that we've taken towards that goal. We're not offering here guarantees that any of these methodologies are going to work in a new domain, but it's certainly something we're excited about seeing tried. Okay. All right. All right, so there's a question here.
Thank you for your great talk. It's very exciting to see combining machine learning and the theoretical economics. Actually, I have a question about the title. That is, I'm trying to understand the motivation of study or focusing on initial play, because usually in repeated game we are more interested in some people may more interested in how the game will converge to a state, for example, after 100 rounds, what will people play? And also, as you have seen that when people are not so familiar with economic game, they may, at the beginning, they are not really aware what they are playing, so they just give some random guess about the result, but maybe after several rounds, they just get a better sense about economic games and play more, do the actions that will more reflect what they are thinking about.
Yeah.
Basically, it's just trying to understand the motivation of just focusing on the initial game.
Yeah, thanks for the question. Okay, so should I repeat the question, or that was heard? Okay. So the honest answer is we really wanted to begin with the simplest possible setting. So because we were trying this new exploration of looking at these black box algorithms and how they're doing and try to build on the theories, we really wanted to keep everything else about what we were doing as simple as possible. An initial play in these 3x3 games is I think a natural starting point from that perspective. So actually Drew and I are also interested in these repeated settings, and it'd be great to see other people try similar things. You could imagine applying these methodologies also to that domain, where you're trying to predict how play will evolve over time. So actually, yeah, that's something we're actively thinking about right now. So I expect it to be more complex. Maybe the results won't be quite as clean as what we've found here, but it's interesting. But also initial play is not unimportant either, in the sense that how people begin actually has implications also for the potential evolution of play after that. And actually, so you're right also that in initial play we might imagine people's behavior to be a little bit more unstructured, exactly because they haven't learned how to interact in these situations. And from that perspective, we might have actually thought that initial play was just all noise. There actually wasn't potential for predicting what people were going to do, and we were sort of positively surprised that there actually is structure, even in initial play, to uncover.
Hi, thank you so much for the great talk. I'm curious to see how you think that this approach can work on empirical efforts to deal with data outside of experimental setting.
Mm-hmm.
So I'm thinking about political scientists. We usually use game theoretical framework to derive hypotheses to be tested in observational setting, and I know that microeconomics also do a lot of this. So I'm trying to, and our approach is generally you have a model, and then you find one possible equilibrium, and then you test in some kind of empirical data. And I'm trying to understand how you can connect this with this kind of efforts to deal also with game theory.
So I don't necessarily see game theory as a necessary point in using these methodologies for political science applications. Let me actually just pause this on the initial slide with the three things that we tried. Okay, right, so these are essentially the three methodologies we see as the techniques that we tried in our domain. And I definitely don't see these methodologies as special to economics. So if you have a different problem, a different prediction problem in political science, you can certainly run an existing model and run a black box algorithm and look at the cases, sort of eyeball the cases where the black box algorithm outperforms your existing model. That would be an application of one. You can also certainly have two models that predict the behavior that you're interested in and try to build a hybrid model that merges those two. I do see these as sort of invariant almost to what exactly you're trying to predict. But maybe that isn't quite.
No, yeah, I was more thinking about because most of the examples that you presented were dealing extracting information from experimental setting.
Mm-hmm.
And I'm thinking how you can expand this to when you're not dealing with experimental data, when you don't have this kind of behavioral economic games that people are playing, and you're trying to test these models on using, for example, observational data. So and you have the hypothesis from the game theory and the game theoretical games.
Yeah.
But I think I got what you're saying.
Well, no, I confess I'm a little bit limited in my answer because I don't have easy access to the specific examples you might have in mind. But let me just. Oh.
I was going to say I have some examples from the Fragile Families Challenge.
Okay.
So So I really enjoyed the talk, and I really enjoyed the way you sort of went through this sequence of approaches. It feels like good detective work that builds on itself. But in the Fragile Families Challenge, we had a kind of a very different result, which was in our setting, the models aren't really clear. So you could say this is the level 1 model. In a lot of the social science settings in sociology, the models aren't nearly as clearly specified. So you would think of those more, maybe you said as statistical models. You didn't like to distinguish
right.
between.
Linear regression model, yeah.
Yeah, it's a linear regression model. And then the second thing, so it's not clear what you would compare the black box model to exactly. There's less of a clear standard to compare to. And then the second thing that we found empirically is that basically all the models make the same kinds of predictions. So some people use a linear regression with variables from the mother.
Yeah.
Some people use random forest with variables from the father and the mother and the school. And pretty much they make the same prediction. And so the idea of building this hybrid model didn't really work because all of the models were essentially making the same predictions. So what I'm wondering is if you have any intuition about what it is about this setting that allows different models to have different kinds of accuracy, or is there something specific about the Fragile Families Challenge that's leading all the models to be basically the same?
Yeah, okay, so two comments on that. So first, right, okay, it's actually interesting that you don't see that problem as starting with a natural class of existing models. So that might be a little bit more specific to economics in the sense that we do have these models that we're really attached to. In particular, we sort of like models that tell stories. And that's one, if you wanted to create this binary classification between economic model and statistical model, that would be one way of doing it, right? So is there a sort of narrative that goes along with your model? Okay, but I take that that's not necessarily present in all domains. For the second thing, right, so actually I remember talking with you about this. I mean, so additionally, before we started this algorithmic game generation, when we just had the lab data set, we actually faced a similar conundrum. Because for this lab data set, everything we were trying was basically producing something very similar to level 1. I mean, actually, if you run a decision tree, the decision tree actually begins with level 1. It first asks, is the action level 1, is action A1 level 1? If not, look at action A2 as level 1, and so forth. And actually, I mean, the gains we were getting, even from the ensemble, weren't actually that large. And again, the ensembles was building decision trees that began with level 1. And so the way that I see that is that those were just instances where level 1 just happens to be a fantastic model of play. But those instances aren't necessarily representative of the whole space. So in this project, it might be that the data that you have access to actually happens to be data where the behaviors are somehow homogeneous and well described by a particular simple model. And then the question that's sort of, I think, important there is, do you think of that data set as then being representative of the whole space, or do you think of that as a data limitation problem, where somehow we just have access to this particular subset of the space, and we really wish we had access also to instances from other parts of the space? And then I see a difference between what we're doing here and what you're probably facing is, here we actually got to generate new instances. I mean, that's pretty special. I mean, maybe not that special, but we basically got to say, look, we only have a subset of games. Let's create new games and go on Mechanical Turk and get new data for those new games. And in this case, that might not be feasible.
That's very helpful. Other questions?
In the first sort of technique that you use, a lot of the gains come from having a smart human analyst look at the cases that weren't predicted well and being able to isolate the features that you might want to define that could help assist the prediction. So the large gain comes from having a smart human analyst. And so I'm curious in settings where that might not be possible, say if the thing that you're looking at is a novel or something where a human analyst can't just look at, a payoff matrix and see what the different features are, how this technique would be modified. Or if there's a setting in which you might start off with a sort of natural low-level representation, like with text data, and rather than a defined set of features that the analyst defined up front.
Yeah, so, okay. I think you might mean that in either of two different ways. So at the end, it sounded like you were talking about handcrafting the features versus automating the features. I do think that there's actually significant gains right now still to using domain knowledge to handcraft the features, again, if you care about interpretability there. But that doesn't seem too much of a problem to me in the sense that people who are interested in predicting something probably have some sort of prior experience with that particular problem domain. Another way in which you might mean your question is this part. When we were eyeballing these payoff matrices and discovering that there was something that looked like risk aversion, right? Yeah, so that part definitely involved a lot of human intrusion and using sort of our understanding of the domain to develop these improvements. Yeah, so I think out of these three methodologies, the first one is the one where I think there's sort of the most hand-holding necessary. It's not just you're letting the algorithm run and do its thing, you're really sort of interacting with it as it goes. I feel like the hybrid model part is probably the one that requires the least intervention by the analyst, right? Because there you can actually, it's really the algorithm is deciding which model to use for prediction, and you're just training that algorithm in a kind of mechanical way. Right? Again, you have to define the features, but then after you've defined the features, the algorithms that we're training to decide model A or model B, that part is sort of, you can just let it go.
Any more questions? Okay, and then I think these two will be the last ones.
I'm just thinking this probably can be like generalized to mechanism design, so you can specify, like handcraft some features of a mechanism, and then you can specify when would the mechanism works, like the conditions when each mechanism might work and induce the result that you wish. Like, is that like a direction you were working on? Or
that would be really cool, actually, and it's not something I've thought about. I guess it depends on what you mean by work. So you mean sort of
like the outcome that you want to induce.
Yeah.
Ex ante.
Right. So I guess the perspective in that literature has been, it works if I can write a theorem that shows that it works under these conditions.
Yeah, yeah.
But maybe if you have in mind sort of producing certain behaviors in practice, then I think we're sort of more operational.
Yeah,
where you might have data on,
and you can specify that, like in the data, from the data.
Yeah. No, that's an interesting idea. Yeah.
I'm sorry that this last question has to be like a really basic question.
No.
But I'm still kind of fixated on like the numbers that are present in a game.
Okay.
So like how the 0 stood out to me, or when there's like, multiples of 10 versus when there's like, I saw one game had like a 7 and like a 33. Does like the kinds of numbers that are in the actual game affect people's strategy?
It's definitely possible. So actually on the zeros, I think we actually restricted the algorithmic game design to not generate any zeros, exactly because we were sort of worried about that being a special number. In practice, I mean, there's a lot of psychological evidence that like round numbers are treated differently from other kinds of numbers. The question really is, can you code that up in a feature, right? So if you have an idea for how to code up the specialness of 7 or 33, right, then we can take that and we can use that as one of our base features, allow the algorithm to use that. And then, and then ideally, in a good case, the algorithm would tell us whether that feature was actually relevant, right? But yeah, for us, we didn't, it's not that we don't think this is what you say is true. And in fact, I'm pretty sure there is some effect, but it's just really hard to formalize what we mean by the specialness of these different numbers. Yeah.
Okay, let's all thank Annie again for working.